In the remote sensing, after the image is captured, an important process is image interpretation, and that for the image interpretation, the resolution of the image should be of high capabilities. Thus, image resolution refers to the ability of a remote sensing system to record and display the final details, including the quality of the data. These details are broadly referred to as resolution, which can be described in terms of time, space, spectral and radiometry. Resolution of a sensor system is its capability to discriminate two closely spaced objects from each other. In this chapter, you will study about the resolution and its types. Resolution. The term image resolution is applied to digital images, film images and other type of images, and it describes the details that an image holds. Resolution can be broadly defined as the ability of a remote sensor to capture and display details of the ground features. In other words, resolution refers to the level of detail to which a ground features can be described and mapped. Resolution varies from sensor to sensor. Resolution is broadly described as coarse and fine. Data having coarse resolution have coarser information, whereas data with fine resolution provide finer details. Resolution characteristics of remote sensing data determine its application potential because data of different resolutions provide different level of details and hence are useful for mapping particular features at a specific mapping scale. The image resolution also depends on the character of the scene that has been imaged, apart from atmospheric conditions, illumination and experience and ability of an image interpreter. Finer details can be seen in higher resolution image. On the other hand, a coarser or low resolution image is one with large resolution size, that is, only coarser features can be observed in the image. Image resolution can be measured in various ways like spatial, spectral, temporal and radiometric. Based on these parameters, image resolution is characterized into four types. Spatial resolution. It refers to variation in the reflectance or emittance depending upon the shape, size and texture of the target. Spectral resolution. It infers changes in the reflectance or emittance as a function of the wavelength. Temporal resolution. It involves diurnal and or seasonal changes in reflectance or emittance. Radiometric resolution. It includes changes in the polarisation of the radiation reflected or emitted by an object. Spatial resolution. Spatial resolution is a complex concept which can, for the purpose of remote sensing of polar regions, be defined as the smallest object that can be detected and distinguished from a point. In other words, spatial resolution is a measure of the sensor's ability to capture closely spaced objects in the ground and their discrimination as separate objects. Spatial resolution of a data depends on altitude of the platform used to record the data and sensor parameters. The most frequently used measure based upon the geometric properties of an imaging system is the instantaneous field of view (IFOV) of the sensor. The instantaneous field of view is the area of the surface that is theoretically viewed by the instrument from a given altitude at a given time. The spatial resolution is usually determined by the instrumental parameters and by the height of the satellite above the ground. With the exception of the active microwave systems, the resolution of a system cannot be better than approximately Hi by d. The diffraction limit, where the h is the height, I is the wavelength and d is the diameter of the object lens, objective mirror or antenna. This limit is typically of the order of 10 to 100 meters for VIS or IR systems operating from satellites in low orbits and typically 1 to 10 kilometers when satellite is geostationary. For passive microwave observation, the resolution limit is much coarser, of the order of tens of kilometers, because the larger wavelength is measured. It is stated that the best achievable spatial resolution is of the order of h by id, except for some types of radar systems. Although some non-radar systems may not reach this resolution because of other instrumental effect. Two important examples are sensors in which the incoming radiation is focused on an imagery array of discrete detecting elements, and photographic systems. The detecting element or film imposes its own maximum resolution, again proportional to the height h, and if this is poorer, then the diffraction limited resolution it will dominate. The spatial resolution achievable by radar system is very depending on the way the data from the systems are processed. Such systems are often pulsed, and one more important factor is the length of the emitted pulse. Synthetic aperture radius (SAS) also integrate the return signal for a period of time while the radar is carried forward on its platform, and the integration time also influences the resolution. It is not possible to give a statement of the general principles determining radar spatial resolution. Spatial resolution of an imaging systems can be measured in a number of different ways. It is the size of the smallest object that can be discriminated by the sensor. The greater the sensor resolution, the greater the data volume and the smaller the area covered. In fact, the area coverage and the resolution are interdependent, and these two factors determine the scale of the imagery. Alternatively, spatial resolution can be said to be the length of the size of the area on the ground represented by a pixel on the image. The basis for the definition of the spatial resolution can be depend on four criteria: geometrical properties of the imaging system, the ability to distinguish between point targets, the ability to measure the periodicity of repetitive target, the ability to measure the spectral properties of the small targets. Based on the spatial resolution, satellite systems can be classified as low resolution systems, medium resolution systems, high resolution systems, and very high resolution systems. Spatial resolution of any satellite sensor applies to the image produced by the system, whereas resolving power of any photograph applies to an imaging system or an component of the system. As mentioned earlier, the most commonly used measure for spatial resolution of any sensors based on the geometrical properties of the imaging system is the instantaneous field of view of the sensor. IFOV is defined as the area of the ground that is viewed by an instrument from a given altitude a given instant of time. For greater clarity of spatial resolution of any remote sensing imagery, it is more appropriate to introduce the term pixel, the picture element. One pixel on a digital satellite imagery represents an IFOV on the ground. Each IFOV is filed by digital number on. Each digital number indicates some inherent property of the terrain element. Spatial resolution of the remote sensing system is influenced by the swath width. Spatial resolution and swath width determine the degree of detail that is revealed by the sensor and the area of coverage. Remote sensing sensors are generally categorized into coarser, intermediate, and high spatial resolution sensors based on the spatial resolution. Sensors have coarser resolution provide much less detail than the high spatial resolution sensors. Because the level of the detail the sensors provide, they are used for mapping at different scales. High spatial resolution sensors are used for large scale mapping, small area mapping, whereas coarse spatial resolution data are used for regional, national, and global scale mapping. Spectral resolution. Different materials on the Earth's surface exhibit different spectral reflectancy and emissivities. The differences, variation in reflectance and emissivities are used to distinguish features. However, the spectral signature does not give continuous spectral information. Rather, it gives spectral information at some selected wavelengths. These wavelength regions of the observation are called spectral bands. The spectral bands are defined in the terms of central wavelength and a bandwidth. For example, a sensor which is making measurements at a green wavelength regions, that is 0.5 μm to 0.6 μm, will have a central wavelength of 0.55 μm and a bandwidth of 0.1 μm. Besides the location of the central wavelength and the bandwidth, the total number of band is also another important aspect of the spectral band selection. The number and dimension of the specific wavelength intervals in the electromagnetic spectrum to which the remote sensing instrument is sensitive is called the spectral resolution. The use of well chosen and sufficiently numerous spectral bands is necessary. It is a width of the spectral band and the number of spectral bands in which the image is taken. Narrow bandwidth is in certain regions of the electromagnetic spectrum allows us to discriminate between various features more easily. Consequently, we need to have more number of spectral bands, each having a narrow bandwidth, and these bands should together cover the entire spectral range of the interest. The digital images collected by the satellite sensors except microwave sensing system like CSAT, CIRBI Radasat have been multiband or multispectral. Individual images separately recorded in discrete spectral bands. Multispectral imaging refers to viewing an area in several narrow bands to obtain better identification and classification of objects. The term spectral resolution refers to the width of the spectral bands. The spectral resolution can be explained by 2 points. The position of the spectrum, the width and the number of spectral bands will determine the degree to which individual targets can be determined on the multispectral image. Second, the use of the multispectral imagery can lead to a higher degree of discriminating power than any single bands taken on its own. Various surface features can be identified by taking these multispectral bands. For example, differences in reflectancy of various rock types are separatable only if the recorded device is capable of detecting the spectral reflectance of the target in a narrow spectral wave band. Radiometric resolution. As the arrangement of pixels describes the spatial structure of an image, the radiometric characteristics describe the actual information content in an image. The information content in an image is determined by the number of digital levels, quantization levels used to express the data collected by the sensors. In other words, a definite number of discrete quantization levels are used to record or digitize the intensity of the flow of radiation or radiant flux reflected or emitted from the ground features. This smallest change in the intensity level that can be detected by a sensing system is called radiometric resolution. It is a capability to differentiate the spectral reflectance emittance between various targets. This depends on the number of quantization levels within the spectral band. In other words, the number of bits of the digital data in the spectral band or the number of gray level values will decide the sensitivity of the sensor. It is the smallest difference in the exposure that can be detected in a given film analysis. It is the ability of the given sensing system to discriminate between the density levels. In general, the radiometric resolution is inversely proportional to contrast, so that the high contrast film is able to resolve small differences in exposure. Low contrast films have greater radiometric range, while high contrast films have smaller exposure range and lower radiometric range. It is commonly expressed as the number of binary digits required to store the maximum level value. Thus, the number of bits required for 2, 4, 8, 16, 64 and 256 levels is 1, 2, 4, 6 and 8 respectively. In an image, the energy received is recorded and represented using the digital number. The digital number is an image may vary from 0 to a maximum value depending upon the number of gray levels that the system can identify, that is the radiometric resolution. Thus, in addition to the energy received, the digital number for a pixel varies with the radiometric resolution. For the same amount of energy received in a coarser resolution image that can record less number of energy levels, a lower value is assigned to the pixel compared to a fine resolution image that can record more number of energy levels. The radiometric resolution of an image system determines its ability to discriminate the very slight difference in energy. Coarse radiometric resolution would record a scene using a few brightness levels, that is, a very high contrast, whereas fine radiometric resolution will record the same scene using many brightness levels. A 7-bit data is considered having coarse radiometric resolution in comparison to 8-bit or 10-bit data. The higher the radiometric resolution of a sensor, the more sensitive it is detecting small differences in reflected or emitted energy. In other words, the higher the radiometric resolution, the better subtle differences of the intensity or reflectivity can be represented. In practice, the effective radiometric resolution is typically limited by the noise level rather than the number of bits of representation. Temporal resolution. In addition to spatial, spectral and radiometric resolution, it is also important to consider the concept of temporal resolution in a remote sensing system. One of the advantages of remote sensing is the ability to observe a part of the earth at regular intervals. The interval at which a given scene can be imaged is called temporal resolution. Temporal resolution is usually expressed in days. For instance, IRS 1A has 22 days temporal resolution, meaning it can acquire image of a particular area in 22 days interval respectively. Low temporal resolution refers to the infrequent repeat coverage, whereas high temporal resolution refers to the frequent repeat coverage. Temporal resolution is useful for agricultural application or natural disaster like flooding, when you would like to revisit the same location within every few days. The requirement of temporal resolution varies with different application. For example, to monitor agricultural activity, image interval of 10 days would be required, but interval of 1 year would be appropriate to monitor urban growth patterns. Land use, land cover classification. Temporal variation in the spectral signature is valuable in land use, land cover classification. Comparing multi-temporal image, the presence of features over the time can be identified and this widely adopted for classifying various types of crops or vegetation. For example, during the growing season, the vegetation characteristics changes continuously. Using multi-temporal images, it is possible to monitor such changes and thus the crop duration and crop growth stage can be identified, which can be used to classify the crop types, that is, the perennial crops, long or short duration crops. Signal to noise ratio. The data recorded on a sensor are composed of signal, that is the reflectance, and the noise, that is from the aberrations in the electronic moving parts of the detects in the scanning system as they degrade over time. If the signal to noise ratio is high, it becomes easy to differentiate the noise from the actual signal. The signal to noise ratio depends on the strength of the signal available and the noise of the system. Increasing the spectral and spatial resolution reduces the energy received or the strength of the signal. Consequently, the signal to noise ratio decreases. Also, the finer radiometric resolution results in larger number of gray levels, and if the difference in the energy levels between the two levels is less, then the noise reliability of the recorded gray level diminishes. Relationship between spatial, spectral and radiometric resolution. In remote sensing, energy recorded at sensor depends on spatial, spectral resolution of the sensor. Radiometric resolution of the sensor varies with the amount of energy received at the sensor. Fine spatial resolution requires a smaller IFOV. Smaller IFOV, smaller would be the area of the ground resolution cell, and hence less energy is received from that area. When the energy received is less, lesser would be the ability to the sensor to detect the fine energy differences, thereby leading to poor radiometric resolution. Use of narrow spectral bands increases the spectral resolution, whereas it reduces the energy received at the sensor in a particular band. The wider band increases the reflected energy. To increase the amount of energy received and hence to improve the radiometry resolution without reducing the spectral resolution, broader wavelength band can be used. However, This would reduce the spectral resolution of the sensor. Thus, there are relation between spatial, spectral and radiometric resolution. These three types of resolution must be balanced against the desired capabilities and objectives of the sensor. Thus, finer spatial, spectral and radiometric resolution of a system may decrease the SNR to such an extent that the data may not be reliable. Summary: sensors are devices used for making observations. These consist of mechanisms, usually sophisticated lens with filter coatings to focus an area observed on the plane in which the detectors are placed. The major characteristic software image in the remote sensing system operating in a visible and infrared spectral bands are described in the terms of its spectral, spatial and radiometric resolution. The spatial resolution is a complex concept which can, for the purpose of the remote sensing of the polar regions, can be defined as the smallest object that can be detected and distinguished from a point. Spatial resolution is usually determined by instrumental parameters and the height of the satellite above the ground. The spatial resolution is achievable by radar system is very dependent on the way the data from the systems are processed. Spatial oscillation of an image system can be measured in different ways. Spectral resolution refers to the width of the spectral bands. Spectral resolution can be explained by considering the position of the spectrum come within the number of the spectral bands will determine the degree to which individual targets can be determined on the multispectral image, and the use of multispectral imagery can lead to higher degree of discriminating power down in single band taken on its own. Radiometric resolution is its capability to differentiate the spectral reflectance or emittance between various targets. This depends on the number of quantization levels within the spectral band. Temporal resolution is ability to observe the part of the Earth's surface in regular interval of time. Temporal resolution is advantageous in monitoring the agriculture or vegetative cover of the surface.